Imagine looking out at the vast cosmos, seeing billions of galaxies, each twinkling with billions of stars, vast nebulae, and swirling clouds of gas and dust. Queen, it seems like a universe teeming with light and matter, a dazzling display. But what if I told you that everything we can see, everything that interacts with light, everything that makes up the stars, planets, and even your own body, accounts for only a tiny, minuscule fraction of what the universe is actually made of? Tonight, on Boring Astronomy, we're going to delve into the unseen, the unheard, the profoundly mysterious components that make up the vast majority of our cosmos, dark matter and dark energy. Last time, we explored the silent genesis of our universe with the Big Bang, understanding it not as an explosion, but as the quiet, continuous expansion of space itself, evidenced by the receding galaxies and the faint echo of the cosmic microwave background. That expansion gave rise to all the visible matter we just considered. But as scientists meticulously measured the universe, they began to uncover glaring discrepancies, realizing that something fundamental was missing from our cosmic inventory. This missing something isn't dramatic. It's just dark, and in its darkness, it reveals a profound uncertainty at the very heart of reality. So, dim the lights, perhaps turn on a fan for that soft hum, and let's ease into tonight's journey together. Let's begin with dark matter. The concept of dark matter arose from a truly boring, yet inescapable problem. Galaxies simply do unbehave the way they should. If they only contained the matter we can see, when astronomers measure how fast stars orbit around the center of a spiral galaxy, they expect the stars on the outer edges to orbit much slower than those closer to the center. Similar to how planets orbit the sun, Mercury whips around fast, Neptune takes his time. This is a basic, predictable consequence of gravity, that familiar force we discussed in our very first episode. However, observations consistently show that stars in the outer regions of galaxies orbit at roughly the same speed as stars closer to the center. This defies the laws of gravity if only visible matter is present. It's like watching a merry-go-round where the people on the outside are spinning just as fast as those in the middle, even though there's nothing obvious propelling them. The only way for these observations to make sense, for gravity to work predictably as we know it, is if there's a massive amount of unseen, invisible material providing extra gravitational pull. This missing mass is what we call dark matter. It's dark not because it's evil or mysterious in a dramatic sense, but because it doesn't interact with light or any other form of electromagnetic radiation. It doesn't absorb, reflect, or emit light. You can't see it, you can't touch it, and it seems to pass right through normal matter without a whisper. It's the universe's invisible glue, providing the extra gravitational scaffolding needed to hold galaxies together and keep them from flying apart. The evidence for dark matter is not direct, but it is overwhelming and comes from multiple, boringly consistent lines of observation. Galactic rotation curves. As just mentioned, the anomalous rotation speeds of stars and gas in galaxies are the primary evidence. Gravitational lensing. When light from a distant galaxy passes through a massive galaxy cluster, the cluster's gravity bends the light, distorting the image of the background galaxy. The amount of bending tells us the total mass of the cluster. Crucially, the amount of mass required to produce the observed lensing is far greater than the mass of the visible stars and gas. This extra, unseen mass is dark matter, bending light with its invisible gravity, much like how a lens focuses light. Galaxy cluster dynamics. Galaxy clusters are groups of hundreds or thousands of galaxies. They, too, require much more mass than is visible to hold them together and prevent them from escaping the cluster's gravitation. Large-scale structure formation. Computer simulations of how the universe's large-scale structure pull formed after the Big Bang only match observations if dark matter is included. Without it, gravity alone from visible matter is unstrong enough to form the structures we see in the observed universe. So, what is dark matter? That's the multi-billion-dollar question in physics and astronomy. We know it's not normal matter because it doesn't interact with light. It's not simply black holes because there aren't enough of them, and their gravitational effects would be different. The leading candidates are exotic, weakly interacting particles, such as WIMPs or axions, which interact only through gravity and perhaps the weak nuclear force. Scientists are building incredibly sensitive detectors deep underground, trying to catch the rare, boring event of a dark matter particle interacting with normal matter. It's an ongoing, silent, cosmic detective story. Now, let's turn our attention to dark energy, a concept even more mysterious, and even more fundamental to the universe's ultimate fate. For decades after Edwin Hubble discovered the expanding universe, astronomers assumed that gravity, the only significant force on cosmic scales, caused this expansion to gradually slow down over time. It's a boringly intuitive idea. If you throw a ball in the air, gravity will eventually pull it back down, slowing its ascent. However, in the late 1990s, two independent teams of astronomers made a shocking, boringly precise discovery. They were studying distant type EAJ supernova, specific types of exploding stars that act as standard candles because they always explode with roughly the same intrinsic brightness. By measuring how dim these supernovae appeared from Earth, they could calculate their distance and, combined with their redshift, determine how fast the universe was expanding at different points in cosmic history. The results were utterly unexpected. The most distant supernovae were fainter than predicted, meaning they were farther away than they should have been if the universe's expansion was slowing down. This is what we call dark energy. Unlike dark matter, which acts like an invisible glue pulling things together, dark energy acts like an invisible spring, pushing everything apart. The only conclusion was that the expansion of the universe isn't slowing down at all. It's actually accelerating. This accelerated expansion demands a new, mysterious force, something that acts as a repulsive pressure, pushing space apart faster and faster. It's not a form of matter or energy that we understand in the conventional sense. It's thought to be an intrinsic property of space itself, a kind of constant, pervasive anti-gravity. What is dark energy? We have even fewer clues than for dark matter. The simplest explanation is Einstein's cosmological constant, a term he introduced into his equations of general relativity to account for a static universe, which he later called his biggest blunder. When the universe was found to be expanding, it seems his blunder might have been correct, but for a different reason. It describes a constant energy density of empty space that drives accelerated expansion. Other theories include quintessence, a dynamic energy field that changes over time, or modifications to gravity itself. The exact nature of dark energy is the biggest unsolved mystery in cosmology, a truly boring frontier of ignorance, driving immense scientific inquiry. When we put it all together, the cosmic inventory of our universe becomes rather humbling, even boring in its simplicity. All the normal matter we can see and interact with, stars, planets, gas, dust, everything in galaxies, everything that makes up you and me, accounts for only about 5% of the total mass energy of the universe. Dark matter makes up about 27%, and the largest component, the mysterious dark energy, accounts for a staggering 68%. This means that approximately 95% of our universe is made of stuff we cannot see, cannot directly detect, and do not fully understand. This isn't a dramatic conspiracy. It's the quiet, perplexing reality of modern cosmology. It underscores the humility required in science, the vastness of the unknown, and the immense work still to be done. Dark matter and dark energy are not flashy cosmic monsters. They are the pervasive, visible forces that shape the large-scale structure and the ultimate fate of the cosmos, quietly, consistently, and profoundly. They are the ultimate known unknowns, pushing the boundaries of our understanding and reminding us that even in the seemingly empty void, there are fundamental drivers at play. So, the next time you look up at the stars, remember that the shimmering light you see is just a tiny fraction of the cosmic tapestry. The universe is mostly dark, shaped and driven by invisible components that defy our direct senses. Dark matter holds galaxies together, and dark energy relentlessly pushes the fabric of space apart, silently, constantly. They represent the quiet, unseen forces that dictate the grand cosmic narrative, making them boring in their elusiveness, yet utterly essential to our very existence. Next time on Boring Astronomy, we'll turn our attention to one of the most exciting, yet often mundane, pursuits in modern astronomy: exoplanets. Searching for life beyond our solar system, we explore the quiet methods used to find these distant worlds, and why the search for alien life is often a long, tedious, and boring, yet profoundly hopeful endeavor.